So my discipline of focus is environmental engineering. And so I'm one of two faculty of environmental engineering. We do have another faculty member, Dr. Bree Dory. And so environmental engineering is really about applying physics, chemistry, and microbiology to protect public health and the environment. And so I want to give an example of how we might apply these different theoretical fields to that end of protecting public health and the environment. So before coming to Gonzaga, I worked for an environmental consulting firm called Corona. We don't have anything to do with the beverage company or the coronavirus for that matter. What I will say though is that environmental engineers do address things like coronavirus. So we try to disinfect water to remove viruses and pathogens. I also just developed an in-class exercise for my environmental engineering juniors that are developing a solution to how we can mitigate coronavirus from being spread in the environment. Okay, so the example I do want to give was from my time working on developing solutions at drinking water treatment plants. So here we're looking at a drinking water treatment plant and then the distribution system that sends clean treated water to people's homes. And so we got hired to help out this water system deal with something they called the black water mystery in the news. And so it was called the black water mystery because when water would leave the water treatment plant, it would exit very clean and drinkable. But for some reason, as it passed through the distribution system, it would leave people's taps looking black. And so we investigated why this was the case, and we found that their distribution system pipes were very corroded, and metals would leach, things like iron and manganese, and turn the water black. And so this is where the chemistry comes into play because chlorine can be added at low levels into the distribution system and react with the iron and manganese and cause it to precipitate and actually stick back on the pipe walls, making the water clear. And then this is where the physics comes into play. We found that they were adding chlorine in their water treatment plant, but because of the way that their hydraulics were set up and the mixing conditions, that the water wasn't getting effectively chlorinated. And so we simply changed the outlet location as well as added in channels or baffles to cause the water to mix with the chlorine. And then this led to the water leaving the tank chlorinated. And this is how we solved the black water mystery. So a combination of chemistry and physics. And so while I don't actually build bridges, but we do have faculty that do that, I think this is an example of one way I try to bridge the theory in the classroom to the real world. And so as was brought up earlier, I think this is something that makes our program really distinct in that we have faculty that not are only experts in the theory and performing research to stay relevant in theory, but we have lots of real world experience and can bridge that theory to the real world in the classroom. And so I'll just touch on real quick some of my research interests. I'm interested in sustainable water treatment, like using something called biochar. That's a filtration material that can remove cancer-causing compounds from water. It's a sustainable material because it can be produced from waste materials. So something like waste wood, we can convert it in something called a pyrolysis chamber to convert it into this filtration media. Also, when people produce heat or energy from biofuels, like this local company to Spokane called Ag Energy, they also produce biochar as a byproduct of producing energy from biofuels. And so I'm working over the next year on a senior design project to determine if the materials they produce as a byproduct is also effective at treating drinking water. And then the last thing I'll say too, our faculty are interested in ways we can apply our different disciplines to support low income and middle income communities. So biochar can also be produced in these types of systems that are used to currently produce charcoal in low income communities. And I've studied ways that we can produce simple systems using just waste materials like food cans to produce biochar. And we found this to be effective in being integrated into simple systems where people might store their water where they don't have access to clean water. And so it can remove these types of cancer-causing substances even in kind of these low-income regions where water is especially polluted.